Well, they use helium now because the hydrogen is too reactive. They actually used to make big flying balloons with hydrogen, and yeah, until it blew up, and then people decided that wasn't such a good idea, and they do it with helium now. Okay. Oh, I guess I should have left that. You've already got that in your notes. Well, let me tell you about one more, and then I'll be done telling you about Lavoisier's experiments. Lavoisier made one mistake, and it's the typical kind of mistake that scientists normally make. Or at least, let's put it this way, it's a very common type of mistake that scientists make. And in logic, it's called hasty generalization. And what that is you see a few instances of something, and you immediately generalize and think it's a valid universal law. Okay? But in fact, it isn't. And Lavoisier did this in one case. He noticed that if he took oxygen and he combined it with carbon in under certain conditions, he could make an acid, okay, a liquid that was acidic. Okay, he noticed the exact same thing with sulfur and the same thing with phosphorus, that he could combine oxygen with these other elements and make a liquid that was an acid. So, what does Lavoisier conclude? That Daniel.
Oxygen with these elements will always produce acids.
Yeah, I mean, he concludes that oxygen is absolutely essential to being an acid. And in fact, that's actually where we get the name oxygen. Lavoisier, a lot of the names we have for elements and the whole procedure for naming chemical compounds comes from Lavoisier. He created the language of chemistry. And he created the name oxygen. In Greek, oxygen means acid former. Okay? So that's actually where we get the name. So you can call this, let's see, Lavoisier's mistake. Let's see. Okay, oxygen plus, here's his experimental evidence is oxygen plus carbon or sulfur or phosphorus gives an acid. Therefore, oxygen is the acid former. Now it turns out that in all these cases where he combined oxygen with carbon and sulfur and phosphorus, it wasn't true that he just had pure carbon, pure sulfur, pure phosphorus. It was a compound that he was working with that also had hydrogen in it. And so in every one of these cases, there was a hydrogen around that Lavoisier wasn't didn't know about or didn't pay attention to. And it turns out that the key to being an acid is having hydrogen, not oxygen. So Lavoisier was wrong on this point. But we're still stuck with the name. We still call oxygen oxygen. But one of the things that you have to notice when you look at the history of science is that once scientists are on the right track and they've got the right method, then it's usually pretty easy for them to catch their mistakes. That a mistake like this isn't really a disaster because the Lavoisier had given chemists, he had put them on the right track, he had laid out the right method, he had come up with a logical language for how to name elements and compounds and so on so that they could actually talk sensibly about what they were doing. And after he did all that, it was easy for the next generation of chemists to catch Lavoisier's mistake. How do you think they caught it? Troy?
Because they repeated these experiments with pure carbon and pure sulfur.
Oh, you could do that, yeah. Actually, the first thing that tipped them off that Lavoisier had to be wrong was they took something that was obviously an acid. It was called mercuric acid. Okay, they didn't know exactly what it was made out of, but it had all the properties of an acid. It was really corrosive and extremely sour, and so they knew it was an acid. It was a strong acid. And one of the chemists analyzed it. Okay? He broke it down, and he found a way to break it down into its elements using Lavoisier's method of analysis. Okay? Lo and behold, he doesn't find any oxygen at all. So here he's got this strong acid, and he can break it down, and it turns out to break down into hydrogen gas and chlorine gas. Okay, another element that they had just discovered. So no oxygen at all. So I mean that's pretty hard evidence that Lavoisier has to be wrong here. And then as they started looking more carefully at all the acids that they knew about and running analyses on them, the one thing they always found in common was not the oxygen, but the hydrogen. So they realized, well, Lavoisier had the right idea. There is one element that is crucial to being an acid. It's just not oxygen, it's hydrogen. Okay. But like I say, notice they catch Lavoisier's mistake by doing chemistry exactly in the way Lavoisier taught them to. So he not only he was the founder of chemistry in the way that Newton, was the founder of modern physics. And even when he made mistakes, he provided his successors with the means of catching them.
What was the acid that the analysts?
Oh, it was. It's actually hydrochloric acid, is what it's called. It's the discovery that blew apart Lavoisier's contention that oxygen was essential to acid was the discovery that hydrochloric acid, it actually equals hydrogen combined with chlorine, and
Are they both just one?
yeah, they actually both just one. So the actual reaction that a later chemist, Humphrey Davy, discovers is breaking down this acid into hydrogen and oxygen. Excuse me, hydrogen. That would be hard to do. And chlorine. Okay. So, all right. That's enough of that. Now, I mentioned that by the time Lavoisier is done, he publishes his major book in 1789. Actually, that's worth writing down. Lavoisier's major book is called The Elements of Chemistry. And that's 1789.
Was he the one who invented the word chemistry, or
No, they already were using that term, but he was the one that really made it into the modern made it a modern science, and he completely reformed the language of chemistry. When Lavoisier came on the scene, there was, I told you, there was no way to distinguish elements and compounds, and people, for reasons that go all the way back to the Middle Ages, a lot of chemical compounds were called crazy things like green lion or star Regulus of Mars. I mean, it was all combined with mysticism and astrology, and Lavoisier wouldn't have anything to do with any of that nonsense. He said, what we need is to start with the substances that we think are elements, okay, that have never been broken down by any chemical reaction that we know about. And he listed these in his book. And he had identified correctly, I think, 21 elements at this stage. Now, he said the way we should arrange our language in chemistry is to call things, name each one of the elements, and then a compound that is made up of, say, two elements, we name it in a way that calls to mind the elements that make it up. For instance, I just wrote on the board, hydrochloric acid. Okay, well, it's pretty obvious that, if I told you this compound is called hydrochloric acid, what are the elements that make it up? Hydrogen and chlorine. Okay, so that's a language that makes sense. If you took hydrogen and chlorine, mixed them together, and called it, green lion of Mars or something, that wouldn't make as much sense. It would be harder to remember too. So Lavoisier completely reforms the language of chemistry. He names these 21 elements. He gives names to all the compounds that immediately call to mind the elements that they're made of. So we have names that make sense. For instance, fixed air became carbon dioxide. Well, if you call something carbon dioxide, it's pretty obvious what it is, right? 1 part carbon, 2 parts oxygen. So Lavoisier lays this out in this book, along with his whole quantitative analytic approach to chemistry and for distinguishing elements and compounds, and we have a full-fledged science for the first time. Now, let me see what. Well, to finish up, how much time have I got?
4 minutes.
Okay. Now, what else is going on at this time? 1789. Lavoisier is in Paris. Nick.
French Revolution.
French Revolution. And I mean, I guess how many of you have studied the French Revolution in your history classes? Do you know? You haven't gotten to that? Okay. Well, the French Revolution wasn't very much like the American Revolution. The best scientist in America was Benjamin Franklin, probably. And he was greatly respected and a part of the American Revolution. Well, Lavoisier was not popular with the French revolutionaries. First of all, they had no respect for science. They didn't value intellectuals, and in fact, and they were against anyone who belonged to the old aristocracy. Okay, well, Lavoisier was born into a wealthy family in Paris, and he was part of the aristocracy. And so after the French Revolution, when the revolutionaries were rounding up the aristocrats and confiscating their property and sentencing them to death in the Reign of Terror, Lavoisier got rounded up. And at his trial, the other scientists in France introduced a petition in his defense, saying how respected he was throughout Europe, what a great mind this was, how much he had contributed to the progress of humanity. And the judge at this trial responded with contempt and said, the Republic has no need for learned men. It was for scholars. And with that, he sentenced Lavoisier to the guillotine, and they chopped Lavoisier's head off in 1794. So that's what ended his career. I mean, he was still extremely productive in science. He was only 51 years old, but he was a victim of the French Revolution. So, but he accomplished a lot before they did that to him. Oh, the Republic has no need for learned men.
We're going to record all the features of this camera and then
Oh.
can't figure out how to use it.
So, I've got my mic on.
Yeah, it's great.
So, okay.
So go ahead.
Okay, so I covered the first couple of experiments that Lavoisier did this morning. The one where he showed that no, in fact, water isn't miraculously turning into a white solid that it leaves at the bottom of the glass when you boil it away, but in fact, it's taking that white solid out of the glass. Then we saw how he burned phosphorus in this container with air, and of course that draws the water up into the container. So the volume of the air has disappeared, as some of the volume of the air has disappeared. And Lavoisier actually showed that about 20% of the air disappears when you burn the phosphorus. But that decrease in the weight of the air shows up in the burnt phosphorus. That, in fact, Lavoisier his principle of conservation of matter is working just fine. That whenever you lose weight somewhere, you gain it somewhere else. And in fact, when things burn, they're taking something out of the air and gaining weight, which is not what you might have guessed at the outset. And nobody, in fact, did guess that. They learned it from Lavoisier. Yeah, Ben.
So the water residue is actually gaining weight?
Well, no, the water in this first experiment, what happened was, people boiled water in a container, okay, and then they saw that after a while they could see this little residue on the glass, okay, and they thought that it actually came from the water, that some of the water had changed into that residue. Well, by carefully weighing, what Lavoisier proved was, no, you have the same amount of water before and after. As long as you're careful not to let the water evaporate away, if you have it in a closed container. You have the same amount of water before and after. The residue has actually been pulled out of the glass. The glass weighs less. Yeah.
I think you need to stress that it's distilled water.
Yeah.
If you boil water in
That's
a pot,
true.
you get that too.
That's true. If you boil water in a aluminum pot or something, or a steel pot, normal water that you get out of your tap, you'll see some residue there. Okay, well that actually does come from, there's stuff in the water. But if you take your tap water and you distill it, in other words, you boil it off and then catch the steam and drain that steam into another container, okay, what you'll get rid of all that junk that's in your tap water, and you'll end up with pure water. Okay, well, Lavoisier started, with pure water in his experiment. He'd already distilled it. So he knew he didn't have anything but water, and he still got that residue when he used a glass container. But he showed the residue actually comes out of the glass. Okay. Nick, did you have a question?
Well, does this work with other materials, like other liquids?
Oh, well, water is more effective at dissolving this stuff in the glass than most other liquids that you might use. For instance, if you used alcohol, I don't think it would work as well. So, yeah, it is. Water's a really good solvent. A lot of things dissolve in water. So that's part of what's going on here. Okay. So, like I say, this is a really crucial result that Lavoisier gets. He understands what burning is for the first time, and it's not releasing something into the air. It's taking something from the air, and it takes about 20% of the air if you completely burn something before the burning will stop. So Lavoisier shows that 20% of the air is the part that burns and the part you can breathe. And the other 80%, they don't know too much about yet, but it doesn't seem to do much. It doesn't react. You can't breathe it. You can't burn it. Okay, now, what's happening in your experiments that you saw last week? You saw the burning of a candle consume some of the air, right? And then you saw the steel wool rusting consume air. So that's the next thing that Lavoisier turns to. He starts looking at rusting metals, and he uses tin and lead and mercury, and a few other metals, and he heats them up in the presence of air, and they, he notices again they take in this 20% of the air. Okay, and so obviously, since it's 20% in both cases, that's pretty strong evidence, right? That it's both the burning and the rusting are using the same part of the air, right? So, sure enough, when he weighs the rusted metals, what does he find? I mean, after they rust, Ben. Yeah, that's right. Right. The rusted metals are always heavier than the pure metals that he started with, and they're heavier exactly by that amount that the weight of the air has decreased. Troy.
Did you ever try to get some of the air like back from the phosphorus? Or, like,
Oh.
did you ever try to get some of it back?
Let me see. I'm not sure that he knew how to do that with phosphorus, but he can certainly do it with the metals. Right, and he does. Now, with the phosphorus, I mean, later chemists would figure out that actually when he burns this phosphorus, it combines into a compound that's 2 parts phosphorus and 5 parts oxygen. But yeah, I don't think that Lavoisier knew how to break this up again and get the oxygen back out. But I'm sure a chemist today could tell you how to do it. I'm not a chemist, so I won't tell you how. But again, it's this, and of course people before Lavoisier had not only had the burning thing backwards, but they'd had the metal thing backwards too. Because what they noticed was, okay, after the metal has rusted, I mean, take the steel wool that you saw rust and take some of the air. The air that's left over in that container with the steel wool, I mean, if you tried to light a match, what would happen? I mean, it wouldn't burn at all, right? And so before Lavoisier, the way people interpreted that was, well, I mean, in the case of a fire, okay, if you've got a candle in some air, it'll use up 20% of the air, right? And then the candle will go out. Now, the way they interpreted that was, well, when you burn the candle, you're giving off this fire substance into the air. Now, the air can only absorb so much fire substance. It gets saturated, and then the candle won't burn anymore because it can't release any more fire substance into the air. Okay, that was the way they thought of it. And so when they realized that after a metal has rusted, you can't burn that air either, they thought, same thing must be going on. Somehow, the rusting of the metal process has released this fire substance into the air and saturated the air, so now it won't burn. But, of course, Lavoisier comes around and shows them the exact opposite is true, that they've had it exactly backwards. You know, the rusting process is not releasing something into the air. It's taking something from the air. And it's taking the part of the air that burns and is breathable, but also the part of the air that rusts metals. And it increases its weight by that amount, and the rest of the air that's left over is this inert stuff that won't burn. Okay. Now, Lavoisier did another experiment that's worth telling you about. Do you remember the guy Black that I told you about, who he was the one that took iron ore and intensely heated it and got a gas off of it. I believe maybe it wasn't iron, maybe it was some other metal, but he got a gas off of it that wasn't normal air, and it was what he called fixed air. Okay, and I told you it was carbon dioxide. Of course, nobody knew that at the time. He just called it fixed air. Well, Lavoisier is the chemist who figures out that the fixed air is a compound of carbon and oxygen, because he actually takes some oxygen and he heats it with charcoal, which is just carbon. And lo and behold, he creates this fixed air that that Black had made. But Lavoisier has done it differently than Black. He's only used two chemicals that, as far as he knows, are both elements, carbon and oxygen. And he's managed to create this this gas that that Black had created. So so Lavoisier by burning oxygen with carbon gets this fixed air. And so he concludes fixed air is a compound of carbon and oxygen. And of course, he always weighs everything, so I'll go ahead and give you the weights too. He finds that, say, 3 grams of carbon combines with 8 grams of oxygen.
Let's start writing down what you actually.
To produce, it will, they will entirely combine and create this gas that Black called fixed air.
Then we also have plastic, okay, as secondary, the most important secondary character. And then we have a whole bunch of them.
Okay.
What is the central current?
So let me go on and tell you about a couple more experiments that Lavoisier did. First, he also repeats the Cavendish experiment, which is, remember that Cavendish combined hydrogen gas. Okay, so how do you get hydrogen gas? Does anybody remember? Troy.
By pouring the sulfuric acid on the iron filings?
Right. Yeah, you can use iron filings. You can use other metals too. But if you pour sulfuric acid or nitric acid actually, on a metal, you'll get a gas bubbling up, and that's this really light gas that Cavendish discovered, hydrogen. And actually, at first, Cavendish thought that this really light gas was the fire substance that everybody was talking about. And he thought that if he combined it with oxygen, he would get ordinary air. Well, of course, he gets water instead. So I told you about that. Now, Lavoisier repeats this experiment, and he shows that if you put these two gases together and then you spark them, Okay, you can ignite them, and there will be this explosive reaction, and you get water out of it. So that's what Lavoisier shows that. So hydrogen plus oxygen gives water. And in particular, he also confirms what Cavendish actually showed too, which was that it's 2 volumes of hydrogen combined with 1 volume of oxygen to get water. In other words, they'll completely react this way. Whereas if you have the same amount of hydrogen as oxygen, you'll have leftover hydrogen. Yeah, sure.
Did he find a way to go from water to hydrogen and oxygen? Or
Did he find a way to go from water to hydrogen? I'm going to tell you about the people. No, Lavoisier didn't do that. Lavoisier did make the statement, though, that ideally, if you want to prove that a certain substance is a compound made up of, 2 elements, say, he said the ideal proof would be this. You can not only take those 2 elements and combine them to make the compound. Yeah, exactly what Daniel said. You can also take the compound, break it apart, and get back to the elements. Okay, now, nobody knew how to do that at this stage. But Lavoisier did make the statement that, ideally, if you really want a really convincing proof, you should be able to go both ways. And it would be a few years before they figured out how. Troy?
the water he got would be distilled water, or
Yeah, absolutely pure water. Right. I mean, the water we drink, has other stuff floating around in it, calcium, other such minerals. But, right, if you just start out with, pure hydrogen and pure oxygen, then you get absolutely pure water. You can start out with, now this is interesting to think about, you can start out with things like iron filings and sulfuric acid. Not good stuff to drink. Okay, and let me see, and a bunch of rusted metal. Okay, and a magnifying glass. Okay, this is what you start out with. You get hydrogen, you get oxygen, you put them together, you spark them, you get water, and you can drink it right down. That's something, huh? Daniel.
They spark it.
Oh, Cavendish actually had a clever arrangement where he used an electrical spark. So basically, he had a wire that he would discharge a jolt of electricity through, and it would cause a little spark in his container of gases that would start the reaction between the hydrogen and the oxygen. Yeah.
How long would it take?
Oh, it happens really fast. I mean, I've never actually watched this chemical reaction, but I assume that it's a flash, and in a matter of a few seconds, the gases have basically disappeared, and you've got a puddle of water in your container.
wouldn't
Nick.
it be like steam instead of?
Well, it depends what temperature you're at. I mean, if you carry this experiment out at a temperature of over 100 degrees, over the boiling point of water, then what you get is obviously just steam over here. But if you carry it out at under the boiling temperature, then you just actually see water in your container. Okay. Now, again, Lavoisier I mean, what else is he going to do? He's not just going to do the experiment, right? He's going to take some measurements. What else? What other question would he ask here about the the hydrogen and the oxygen and the way they combine? Daniel.
The two of them separately should equal the water.
Yeah, absolutely. Well, the weight of the hydrogen and the weight of the oxygen should add up to the weight of the water. And he verifies that, and that's true. But he's also interested in something else. What is the weight of hydrogen that combines with oxygen to produce water? And what's the ratio of the weights? And he finds that, again, that, let me see, say 8 grams of oxygen combine with 1 gram of hydrogen to give water. So you can see, I mean, hydrogen's really light compared to oxygen, because, I mean, if you had these two gases in containers at the same pressure, and let's say you had 1 liter of oxygen and 2 liters of hydrogen. Okay, they would completely combine to form nothing with water, to form water with no leftovers. But the 2 liters of hydrogen would weigh 8 times less than the 1 liter of oxygen. So hydrogen is really light stuff. That's why if you put it in balloons, it'll float, right?